Okay? And now the great thing comes. Well, when I write down what are the proofs of all of these things, I'm going to need this structure of multiplication and inverses and reflexivities in, say, the loop space. Okay? That's what's going to happen. To define alpha requires, in the loop space, inverses and concatenations and reflexivities will be used in the loop space. So then the question is, what laws should those things satisfy? That is, if I have two paths, alpha and beta, maybe reflexivity and some composition of something with its inverse, those are alpha and beta, are paths between paths, well, then they should satisfy the groupoid laws too, which means there should be a higher homotopy, which I'll write with 3 arrows, that looks like that. Or if you can picture this structure, you can take 2 copies of this and put them in 3 dimensions, and then there's a, what's the word to use? There's another face. The terminology people use is face because they run out of words. There's a face between faces, okay? These edges, in the low dimensions, you have good names. These are vertices, these are edges, that's a face. But now what about faces between faces? We need a word for that. Pretty soon we run out of words, so we just call them all faces. So there's going to be a face between faces, which is a yet higher homotopy. So what this means is that you get all of the groupoid laws up to higher homotopy, 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 all the way to infinity. And this is called the structure of a weak infinity groupoid. That is, you have the structure of the groupoid that satisfies the groupoidal laws up to higher homotopy. So when I first learned about this, I thought, Jesus, I asked Peter Lumsdaine, I said, yeah, but it sort of means like nothing ever really holds. It only holds up to a bigger lie. Okay? Okay. You sort of say, well, these things don't really hold. They only hold up to a bigger thing. And then, oh, well, those aren't really having the groupoid laws. They only hold the groupoid laws up to an even bigger lie. And the way it works is, as long as you carry those lies to infinity, you'll never get caught. It's a Ponzi. It's a Ponzi scheme that never runs out. Okay? So I asked Peter, I said, Peter, Jesus, I mean, does that make sense? And he smiled and he looked at me and says, well, what could go wrong? And I said, well, you know, that's a really good question. I don't know, but doesn't that feel odd to you? That somehow, I don't know, it's a psychological thing, but in a certain, it's not well-founded. There's no spot where something utterly becomes true unless you truncate. So the idea is that we're going to talk about something called truncation. So an example of it is, if I demand that these hold up to definitional equivalence, then I will have what is called a strict groupoid. So you can strictify or truncate, as it's called, at any dimension you wish, and demand that, no, at that dimension I demand that these things really hold on the nose. So that's the terminology. There are scenarios where that is the appropriate thing to do. In particular, to use the notation of what we will call, eventually we will call the fundamental group, which you might have run across before, the fundamental group of a space, in homotopy type theory is the truncation of the loop space. It's usually of a fundamental group is usually defined for a based space, but we'll say the fundamental group of a space at a base point A is the zero truncation of the loop space. What it means is that we collapse all the higher structure down to a point. Okay, and treat them as identical, not just merely equaled up to higher homotopy. And that fundamental group that's like the starting point, okay, for algebraic topology. That's like one of the most basic constructs in algebraic topology, is the notion of a fundamental group. And it can be defined in higher homotopy theory. I haven't really said what this is, but this is the zero truncation, which says treat it as having a strict group structure. Because when you're working with loops, then a groupoid is just a group. And so this will have the structure of a group like you've seen in math. And what Dan is going to prove for you, and he'll show you, is if you take A to be the homotopical circle, the fundamental group will be the integers, all right, under addition. And that's the concept of a winding number, which you probably ran across in like complex analysis maybe, okay, would be a typical place to see it. The notion of the winding number of a curve. How many times does it go around some point? You will see when Dan lectures, he will tell you about the fundamental group of the circle. And we'll get to that. So I'm going to stop there. So what I'm going to pick up next time is this picture. Okay, I'm going to talk about transport and the notion of a fibration, and I'm going to say a little bit about what are called higher inductive definitions, because I can use this interpretation of the identity type as representing paths in a space to represent higher dimensional objects like the 17-dimensional sphere. Okay, this will be possible to define in homotopy type theory. I'll show you how to do that. And that is a remarkable thing for several reasons, one of which is a very beautiful inductive definition, and moreover, it suggests, we haven't gotten there yet, but it suggests that we will be able to open up the theory of computation to work on objects that have hitherto never been considered as objects on which we compute. So we'll be able to talk about if everything works out. This part is programmatic rather than a result. Programmatically, it will work out that we'll be able to talk about computable functions from the 3 torus to the 4 sphere. That will make perfect sense. If this works, it would be it's the most adorable thing I can think of, okay? Because you have then, at that point, extended the realm of computation to reaches that have never been considered before. So, people often talk about the Turing tar pit, but the reason is that if you consider only functions on the natural numbers, it's true, you're not going to get anywhere. Nothing you're ever going to come up with, I predict, it's Church's law, will ever get you anything new. But it doesn't say anything about when you work with types other than that. So somehow, conventional computability theory is stuck on the natural numbers. They don't know about other types. So we've gone ahead, we have lots of types. And now pretty soon we're going to have types that correspond to these geometric, or I would rather say topological structures, and have notions of computation over them, so that we can in fact have more expressive programming languages. It's just in a different axis from n arrow n. If that works out, that's my hope. I hope by the end of my career that's all true. That's what I am working on. Okay, so enough for today. Sorry I ran over time.